Hello everyone. Today, we're going to learn how to use Xilinx Vivado for simulating a lab experiment. This is particularly useful for students in the CMOSVLSI Design Laboratory, part of the BTech third year second semester curriculum. We'll be realizing all the logic gates using Verilog in Vivado. This includes writing RTL code, creating a test bench, and analyzing simulation results. Let's dive in. Before we dive into Vivado, let's get our files organized. First, I want you to create a dedicated folder where all our project files will live. Let's name this folder lab_01_simulation. You can create it on your desktop, in your documents, or anywhere you prefer. Next, open Xilinx Vivado. You'll find it in your Start menu if you're using Windows, or in your Applications if you're on a Mac. Once it's open, you'll see the home screen. We'll start a new project. This is your first step into designing logic gates. Choose a project name and location of the lab_01_simulation folder. For this experiment, let's name our project Logic Gates Simulation. Select the RTL project option and ensure Do Not Specify Sources at this time is checked. We'll add our Verilog files shortly. Finally, we shall continue with the default device. Now, it's time to add our Verilog files. Click the plus button in the Sources window. Choose Add or Create Design Sources. Now click on Create File. Specify the file name as logic_gates.v. We shall not use automated code generation and hence click on Cancel button. We shall write our own code for logic gates. Now, let's start typing our RTL code. This code is the core of our project, where we define all our basic logic gates, and, or, not, NAND, NOR, XOR, and XNOR. First, we declare our module named logic_gates. This module will have 2 inputs, A and B, and 7 outputs corresponding to each logic gate we're realizing. Remember, in Verilog, inputs and outputs are declared with input and output keywords, respectively. Now, let's implement each gate. We start with the AND gate. The assign statement creates an AND gate by logically ANDing inputs A and B. Follow a similar pattern for the OR gate using the operator. For the NOT gate, we only need one input, so we'll use assign NOT_gate_A equals A to invert input A. Then, proceed with NAND, NOR, XOR, and XNOR gates using the AND and caret operators as needed. These operators help us define the logic for each gate easily. After typing out the logic for all gates, ensure you close the module correctly with an end module statement. This tells Vivado that we've finished defining our logic_gates module. Now, let us repeat the process of adding the file for the test bench code, but this time choose Add or Create Simulation Sources. Our test bench file is named logic_gates_tb.v. The test bench is where we simulate different inputs to our logic gates and observe the outputs. It's like a virtual lab experiment. Open the test bench file. Start with the timescale directive at the top. This sets our simulation's time unit and precision. For our purposes, 1 nanosecond by 1 picosecond is perfect, offering a nice balance between simulation speed and detail. Declare the module for our test bench logic_gates_TB, without any inputs or outputs. Here, we use reg for our inputs A and B since we'll be changing their values in the simulation. The outputs are declared as wire because they are driven by the logic gates within our RTL module. The heart of the test bench is instantiating the unit under test, or UUT, which is our logic_gates module. Connect the inputs and outputs accordingly. This is where our test bench starts to interact with our RTL code. With everything set up, we'll write the initial block to drive our simulation. This involves setting different values for inputs A and B and observing the change in outputs. Remember, use hashtag to specify the delay in nanoseconds for each test case. Once you've written the test cases and observed how the gates behave under different inputs, end the initial block and close the test bench module with end module. And that's it. You've prepared both the RTL code and the test bench for simulating logic gates. With our files added, it's time to run the simulation. Click Run Simulation and run Behavioral Simulation. This tells Vivado to simulate our logic gates using the test bench as a reference. You'll see a waveform window pop up. This shows how each logic gate behaves over time according to our test bench inputs. It's fascinating to see your logic gates come to life. Click on Zoom All button to see the full waveform. On the menu bar, click on the Restart button to go to Start of Simulation. Set the simulation time to 200 nanoseconds and click Simulate button as shown. We can see the waveform again. Use the waveform to verify the relation between the inputs and output of various logic gates. As the code is working as expected, let us synthesize the design by clicking on Run Synthesis. Running synthesis in Xilinx Vivado converts your HDL designs into a format that's compatible with FPGA hardware. It streamlines your design by optimizing logic, reducing the FPGA resources required for implementation. The process intelligently assigns your design's logic to specific FPGA resources, like logic blocks and I/O pins. Through timing analysis, Vivado ensures your design will operate correctly at the desired clock speeds. Early in the design phase, synthesis detects potential errors, allowing for timely corrections. A netlist is created, outlining how each component in your design connects, setting the stage for physical realization. Vivado synthesis applies power optimization techniques, making your design as energy efficient as possible. You'll receive detailed reports on how much of the FPGA's resources your design will use, guiding possible design adjustments. After synthesis, you're provided with a comprehensive report that details optimization results and performance metrics. This critical step prepares your project for the subsequent phases of FPGA development, like placement and routing, moving you closer to a finalized design. After successful synthesis, the user is prompted to run implementation. Click on OK to proceed. Running implementation in Xilinx Vivado takes the synthesized design and maps it onto the physical layout of the FPGA. This phase involves placement, where Vivado decides the exact location of each component within the FPGA's architecture. Following placement, routing establishes the physical connections between components, ensuring signal integrity. Implementation optimizes the design for performance, striving for the best possible speed and efficiency. Vivado conducts a series of checks during implementation to ensure compliance with timing constraints, crucial for reliable operation. Power analysis is integrated into the implementation process, allowing for adjustments to minimize energy consumption. The tool provides detailed reports post-implementation, offering insights into the physical layout and performance metrics. Design rule checks, DRC, are performed to verify that the FPGA design meets all specified requirements and industry standards. The outcome of the implementation phase is a fully mapped design, ready to be loaded onto the FPGA for testing and deployment. This step is pivotal, as it transitions your project from a theoretical design to a tangible, operational FPGA configuration. After successful implementation, the user is prompted to open implementation. Click on OK to proceed. Go back to Synthesis section and click on Open Synthesized Design. Opening a synthesized design in Xilinx Vivado allows you to visually inspect and analyze the logic and resource allocation before moving to implementation. This step provides insights into optimization outcomes, showcasing how your HDL code translates into FPGA architecture. By clicking on Schematic button under the Open Synthesized Design will allow you to see actual implementation of your RTL code. It enables the verification of component placements and connections, ensuring they align with the intended design specifications. Viewing the synthesized design aids in identifying potential areas for further optimization or adjustment, improving overall efficiency. This critical review phase is essential for troubleshooting and refining the design, setting the foundation for successful implementation and deployment. After checking the schematic, we can go and click on Report button given under General window to see the various reports generated during synthesis. Next, click on Report_Utilization. The Report_Utilization command in Xilinx Vivado provides a comprehensive overview of how your design uses the FPGA's resources, including logic blocks, memory, and I/O ports. It helps identify areas where the design might be optimized to reduce resource consumption, ensuring efficient use of the FPGA. This report is crucial for understanding the scalability of your design, allowing for informed decisions on FPGA selection and future design adjustments. Upon scrolling further, we can see other reports generated during implementation and synthesis cycles. Scroll down to see the power consumption report. Finally, click on the Summary tab to see the resource utilization and other results. This concludes our experiment of realizing logic gates using Verilog. That wraps up our journey through creating and simulating logic gates in Xilinx Vivado. We've shown you each step to get your lab experiment up and running. Remember, experimentation is key to mastering digital design. If you enjoyed this tutorial and learned something new, give us a thumbs up, share with anyone who might find it useful, and subscribe for more tutorials. Happy designing, and we look forward to seeing what you create next.